Hey everybody, welcome back. I am Chili and this is lesson 4 of the SSE hand relief series. That's a Borat reference, by the way. Today we're going to be talking about alignment. And alignment is one of the things I like to classify as dumb bullshit. Now there's a lot of stuff that I say is dumb bullshit, but this truly is the dumbest of all the bullshits. Now, let us waste no time and get started here. Now, one thing you might have noticed about the SSE series up until this point is every one of the filters that we've been working with, they've all been full screen. And this is by design because if you have a full screen filter, you don't have to worry about alignment because everything starts at the beginning of the surface, and as long as the surface was allocated such that it is aligned, then your full screen filter operations will all be aligned as well. However, if you want to do something on a smaller region of the screen, like for example, you want to draw a rectangle, an arbitrarily sized and positioned rectangle somewhere, you are in general not going to be working with aligned pixel values in the start of your drawing. And that's going to cause you problems because, as I've mentioned before, SSE likes to have its stuff aligned 128 bits or 16 bytes. So let's get a little start on this tutorial. We're going to try to draw a rectangle using very simple algorithm here. Draw rect SSE bad. So simple, very simple, takes a rectangle structure, a reference, constant reference, and a color. And then it draws the color to that region on the screen. So all we're going to do here is we've got our outer loop, which is just looping the Y variable. Our inner loop, which is looping the pointer that goes along every row. And then we're storing 128 bits at a time. Quite simple. I hope I don't need to explain all that at this point. So we go graphics.sysbuffer.drawRect SSE bad. We need to give it a rectangle. So let's go with something simple. I think my rectangles go left, right, top, bottom. So 16, 32. Let's go 32, 64, and we'll go 50 to 101. Some random numbers there. Not quite as random as all that, but still. And the color we'll use is a nice green color. I'm feeling green today. So we'll build that and we'll see how it goes. Start without debugging. And as expected, we get our nice green rectangle here. Top left-hand corner. That's all good. What if we try to shift over this rectangle by just one pixel to the right? I'm going to put this in debug mode and run it again. And what do we get? We get access violation reading location blah 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 bitty blah break. Why? Because we are trying to store to an unaligned memory address. I don't know why it says access violation reading from. It's probably some bullshit that the debug code puts in there. But at any rate, the problem lies in the fact that we are not aligned. So, what can we do to get aligned? Well, if we look at, let's take a look here. Imagine this is our a row of pixels that we're writing to. By the way, note that alignment, the Y direction doesn't matter at all, right? That doesn't make any difference. It's only the X direction that you have to worry about alignment in. Because the Y is just separate rows, and every individual row is always going to be aligned. It's just the pixel in an individual row, whether it's going to be aligned or not. Not the pixel, but the 4 pixels. You get what I'm trying to say. The group of pixels. The double quad word, I believe is what you call those. But anyways, so let's say we're going to try to draw this row of pixels into a surface, into memory. So I've got these pixels labeled. This is not the byte count. This is not the pointer values. This is the pixel count. So every 4 pixels here is actually 16 bytes. But we don't have to worry about that. We want to align to every 4th pixel. So what we're going to do is, if we try to draw, like, this is the thing that we're trying to draw here, the line or whatever you want to fucking call it. It is 8 pixels wide. So that is 2 SSE store operations. Correct. So far, so good. Now, if we try to do that, if we try to store, first we'll try to store this one. The problem is we are not storing to an aligned section of memory, so we're gonna get our program is gonna crash. It's gonna shit the bed, as I like to say. So, what do we do about this? The solution is quite simple. It has a name, and the name is called, what's it called again? Loop peeling is what it's called. Loop peeling. So what loop peeling is basically breaking up a loop into several smaller loops such that shit works correctly. Specifically, in our case, this part of the storing and this part of the storing here is not going to be aligned. This part, the middle part, will be aligned. So what we do is we break down the storing loop into 3 loops. First, in the pre-loop, we store this single pixel. Then in the mid-loop, we do an SSE store. This store here is just normal. So this would be scalar, vector, and then here's a loop of 3 stores of scalar pixels. And if we do that, then we're all good. We don't have any problems. What does that look like in code? Well, let's take a look at direct or draw SSE without the badness. And we see we have 3 loops here. So we calculate, what do we calculate here? Let me just take a look at what I have written many moons ago. So we're going to calculate some pointer values. These are end peel, end loop. Why do I have it like this? I don't know. Start loop. What do we got here? Okay, so actually the function starts up here. I wasn't even looking at this part here. So what are we going to do? C128. So we create a, this is the same as up here, right? Yeah, we just take the color value and we fire it into all 4 color positions in the XMM register, the SSE register. That's no problem. Here, we want the start of the loop, the end of the loop. So this is finding the start of the aligned portion and the end of the aligned portion. Could have named these variables a little better, like start aligned, end aligned, but whatever. Doesn't matter. So here, what we're doing is we're adding 3, and then we're taking the modulus of 4. This is a fast way of getting the modulus of 4. Or this is the fast way of getting the modulus of 4. So what we do is we add 3 to bump it up to the next value, and then we drop down to the mod 4. For example, taking a look at this. So here our position is 3. We add 3 to that. 1, 2, 3, we get 6. And then 6 mod 4 equals 4. So this finds, from any starting position, it finds the beginning of the aligned portion. And the same with this one here. What do we do here? Let me take a look at our good old friend. Yeah, here. We just, we end with this value here, and that drops it down to its nearest 4th aligned position. So this here, it's not like I said before, it's not mod 4. It's rounding up to the nearest, if we add 3 and then end with this, we round up to the nearest 4th aligned position. And if we just end with this, we round down to the nearest 4th aligned position. So we're just, basically what we're doing is we're taking the whole range here and we're squeezing it down to just the aligned portion. We're cutting off the unaligned end trimmings, if you will. All right, so P end peel here is calculating the end of this first loop here, which just handles the trimmings on the beginning. And so we calculate the end of this loop, and for some reason that I can't understand, I also calculate the end of the vector loop here. And then we start the peeling loop at the start of our rectangle, and we're going from the current value until the end, and we just increment the pointer, and we store our color into the memory there. Very simple. Now here, what we're doing is we're going to cast our values to SSE pointer values, and we're going to go from we're going to start at the end of our last loop, the P end peel, and we're going to go to the end of this loop, and we're just going to increment the M128 pointer, and we're going to do vector stores. And then at the end, we're going to start at the end of this loop. And this loop is going... Let me think here. What is this? Oh yeah, so this is pointer to P current. And the end of this loop is going to be the end of the rectangle. So just the rectangle.right, which is the X value, plus the pixel pitch times the Y of the current line that we're writing. And yeah, again, same, just a bunch of pointer bullshit, pointer arithmetic, because it's faster, but it's also harder to read and a little more difficult to write, which is why I only do the pointer bullshit on the inner loops, and on the outer loop, I just loop on the actual index, or the actual coordinate, the Y coordinate. So let's take a look at how this runs. Remember, this SSE bad crashed on this code. Let's see what SSE not bad does. It works fine. No problem. Because we handled the unaligned portions at the beginning and the end of the rectangle with loop peeling, we have success. We have succeeded. Very simple. So that wasn't so hard, right? What was Chili talking about, all this dumb bullshit? I don't see bullshit that is quite that dumb. Well, wait first, because we've got lots more to go over here. What we've got here is now we're going to try to blit from one surface to another surface. So we're going to try to copy. This would be surface 1. This would be a single row of pixels for surface 1. And here is a corresponding row of pixels in surface 2. And we're going to try to copy from here to different locations, just as you would generally do in a blit operation. Now, The problem with this, well, let me illustrate with some fancy drawings. So what we might want to try is, okay, well, loop peeling worked great last time. Let's try that again. So what we'll do is we'll draw this pixel here. We'll draw it with just your standard scalar operations, and the end pixels here we'll also draw with scalar operations. And now the internal part, the aligned part, we can just load this with SSE loads and then store with SSE store. Only, oops, we can't do that because, well, I mean, look at it. If we load this block here, this block corresponds to, let me just get some different color here. That corresponds to these pixels here. This goes to here. But if we try to store this with SSE store, we'll get, you know, our compiler is going to puke. Not our compiler. Our compiler won't give a shit, but our computer will puke because it can't store to this unaligned address. Not for SSE. So you might say, well, Chili, I got you. I know what we got to do here. Before we had only one surface, the destination. So all we had to do was peel for the destination. But now we've got the source and the destination. So what we got to do is we peel for the source, and then we peel for the destination. Well, let's try that. Let's peel at the destination here, and we got to peel this off here. And so this will now be scalar stored as well. So we're going to do that, and we're going to do that. And oh shit, well, now we've got this aligned bit here, but the corresponding source is again unaligned. So you can't use peeling to solve this problem because the source and the destination are unaligned to each other, if that makes sense. They are out of phase, so no amount of peeling is going to correct that. It's not just a problem of fixing up the ends and then you're good to go. The problem lies throughout the whole operation. And so you're not going to be able to just fix up the ends and Bob's your uncle. That's what I'm trying to say to you. So what you got to do is, let me think about how I want to word this, how I want to explain the situation. Well, let's take a look very simply at, screw that. Let's take a look at what you would have to do to store to a single position here, to a single aligned position in the destination. So this will be our base. Okay, let's say you want to store to a single aligned 4 pixel location here in the destination. So what source pixels correspond to these 4 destination pixels? Well, we've got 2 pixels here, so we got 2 pixels here. So that means that these 4 pixels correspond to these 4 destination aligned pixels. So what you're going to do is you're going to load these 4, and you're going to load these 4, and you're going to combine them to create these 4 here. So let's take a look. Let's give them names. We'll call this one A, B, C, and D, and we'll call this let's see, W, X, Y, Z. Now, our final result is going to be B, C, D, W. So how do we get that? Well, what you do is you load A, B, C, and D. And you're going to want to shift this one left by 1 pixel, so by 4 bytes. And that'll give you, so shift left 4, and that'll give you B, C, D, and nothing, 0, empty, nada. Now for this one here, W, X, Y, Z, we're going to shift this one right by 1, 2, 3 pixels, which is 12 bytes. And that'll give you 0, 0, 0, W. And then what you want to do is you bitwise and you bitwise OR these together. And bitwise OR 0 and anything is just your anything. So you're going to get B, C, D, W, which is what you want. And then you can store this directly in your result position. And that's about it. And what you do then is you say this is your say this is your old, this is your new. Okay. So you combine old and new with some shifting and ORing, masking if you will, to get the combined result, and you store that. Then this is, don't need this anymore. New becomes old, and your next 4 pixels are now new, and you do it again here. And you just keep going along until you get to the end. Now, the beginning and the end are a little different. All right, so let's take a look at some simple situations for blitting with SSE. So the simplest that you can conceive of is the source and the destination are both aligned. So your source rectangles, your left and your right, are aligned. And your destination point, the X value, is also aligned. So all you got to do then is you calculate your pointer for your source, your end pointer for your loop, which is just your pointer for your source, plus the width divided by 4. And you're dividing by 4 because your loop is going to be looping on your source is a 128-bit value, so that's 4 pixels, but your width is just a single pixel value. So you got to divide by 4 to get your width in SSE chunks. And then you add that SSE chunk count to your original pointer to get your end pointer. And the destination, again, is just simple calculation. We've done this all before. And you do your load and your store, and it works fine as long as both your source and your destination are aligned. However, if they're not aligned, bad shit happens. So, the next simplest situation that you can look at is the source aligned situation. Now, in this situation, we assume that your source rectangle is already aligned to SSE memory requirements. So in that case, all you've got to do is handle the alignment with respect to the destination. So what we do here is we mod the destination point X by 4, and then we use a switch statement, and we just change what we're doing depending on the alignment value. So in alignment 0 means that the destination is also aligned, and then we just do this stuff here. All I did was I copied this body basically into here, and that was it. Now, for the other cases, we don't have alignment, and so we've got to do the stuff I was talking about before, which is to say that here we're looping through the y values, and so here we get pointer to the source, divide by 4, round down. So what we're doing here is we're not really, it's kind of loop peeling, but it's not really. Yeah, it's a bit of a doozy. Well, the source that we're loading here is just going to be the actual pointer calculation. There's no adjustment going on because this is source aligned, as we stated up here, blit source aligned. So there's nothing fancy going on here. Just load the pointer to the first pixel. And the end is again just divide by 4 to get the chunk count of the width. Add that to the starting pixel pointer to get the end one. Now the destination, we have to in this one we're rounding down to the nearest 4 aligned address. And again, we use this to round down to the nearest 4. And then we start our bullshit. Now what's going on here, the idea is we're going to start storing to here. So, well, this isn't actually correct because our situation as it stands is more something. Yeah, gotta get rid of all this bullshit here. Excuse me while I adjust my diagram ever so slightly. So our source is aligned. Our destination is not aligned. So our destination is just going to be up to here. And this is actually nothing. So forget about it. There. Beautiful. All right. So our source, we're going to start loading from here. We're going to do 2 loads and we're going to store. Now the problem is we can't just load this and store it to here because that's not the way it is. These pixels belong here and these pixels belong here. So what we're going to do is we are going to prime the pump, as to say, to get our engine started here. We're going to load the original value of the destination here. So let's say that this is A, B, C, D. We're going to load this one here, and then we're going to shift it right. Here we have alignment, destination alignment of 2, right? This would be 0. If it was here, this would be 1. This is alignment value 2. So we're going to shift right by 2. We'll get 0, 0, AB. And this is W, X, Y, Z. So now what we do is we load W, X, Y, Z. And then we proceed, as I mentioned before, in that this one is going to get shifted left by the alignment value, which is 2. So we'll get AB 0, 0. This one is going to get shifted right by 4 minus the alignment value, which is also 2. So we'll get 0, 0, WX. Then we will OR them together, and we will get A, B, WX, which is what we want in here. We want the original values here, and we want the blit values in here. So we composite this original block and the source block to get the final destination block here. And then we proceed as before. So this was new. This value here, the pre-shifted to the right value, was old. Old gets discarded. New becomes old. This becomes new here. And we'll get G, H, J, K, I don't know, whatever. And so then we will, for this one, shift left by 2. We get YZ. This one, shift right by 2. We get 0, 0, GH. We OR these together. And that gives us YZ, GH. And that's what's gonna go into here. Y, Z, G, H, which is what is supposed to go in there. So, and then pump continues. Discard this. This becomes old, and this becomes new, only we're done, so we don't actually need to do that. But that's the general idea. Now, at the very end, we have a problem here. And the problem is we're going to store JK into here, but we have to leave these values the same. And we handle that basically the same as we handled the beginning. We first preload the destination values into a register, and then we composite them with the source values and write back to the destination. So that is how it is done. So here's how it is actually done in code. The first part that I talked about, I call that priming the pump. And so we, our old and our new is going to be, what is it going to be? Previous and new source. So we got previous source and we've got new source. So we load the first, in the beginning, previous is going to be the destination pixels. And they're going to be shifted left by 12. This is case 1. So we're shifting these ones, pre-shifting them left by 12. Does that make sense? I think it makes sense. I'm going to say it makes sense because it works. And then when we enter the loop here, this is where we do the actual writing. We're going to load the new source from the source. And we're going to combine the previous source shifted right by 12 and the new source shifted left. Okay, I understand now why I'm getting mixed up. And I always do this bullshit. It's something that I fucking hate. But when we write pixels onto the screen, the lowest pixel here is going to be on the left. And as you go right, the pixel values increase, right? The pointer values in memory increase. But shifting right means shifting to the low side. So this, if you have a value or a register of 4 pixels that you loaded from memory and you shift it right, you're actually moving the pixels left on the screen. Because when you write a binary number, right, 0000001, this is the low, this is the high. So the high goes on the left. But when you're actually drawing pixels on the screen, the higher order pixels go on the right. So it's opposite, and that's what fucks me up. And I have written so many freaking bugs into my code because I got my right and my left mixed up. So Chili can't tell left from right. That's the moral of this story. Don't do like Chili do. And so when you want to move pixels left, you shift right. And when you want to move pixels right, you shift left. It is seriously dumb bullshit, as I've stated before, but it has to be done. So that is why we are shifting left here to prepare our pixels, prime our pump, and then when we actually put them together, we shift right, we shift left, we OR them together, and we store. And we keep doing that until we get to the end of the aligned portion. And when we're at the end of the aligned portion, previous source is going to contain the last block of source pixels loaded. And what we're doing then is we're going to combine that previous source with the pixels that are here to get the final block to be stored. And that is done basically like this. We have to load the destination pixels, and then we shift right, and then we shift left. And what shifting right and then shifting left does is, if we refer to our diagram here, our final destination block is going to contain, pixels A, B, C, D, but we only want C and D. So by shifting right, and this is shifting right, and then shifting left back, we end up with something like this: 0, 0, CD, which is what we want. And then we shift our old values. Where do we shift them? We shift them right to get them over here, and then we OR them with this. And yeah, here we go, shifting right by whatever amount we need to, and we OR them with the right left shifted destination values, and we get our final value to be stored. And that is how you process a row when the source is already aligned, but the destination is not aligned. You break it down into 4 cases, and you process those 4 cases. Now, this is very nasty. We've got a lot of repeated code here. In fact, the only thing that changes really is these shift values here. This value 8 here, and down here, the value is going to be 4, 4, and basically the complement, which is 12, right? 4 plus 12 equals 16. Here it's 8 and 8 because they're the same. Here it's 12 and 4. You get the idea. That's the only thing that's changing. So you might say, well, Chili, why don't you just make a function for all of this code here? Make a function where you pass in the alignment value, and then you can do your bullshit. And there's a problem with that, and that is that these functions here, for example, the shift left, this value has to be a constant that is known at compile time. The compiler has to know this number while it's compiling. It can't be a number that is derived at runtime. But function parameters are derived at runtime, so it's not compatible. You can't write a standard function to do this bullshit because it contains values that have to be known at compile time. Now, C++11 has something called constant expression, which is a way you can specify a constant value whose value is known at compile time. But the compiler that I'm using right now, or the environment, which is Express 2013, has not yet implemented that feature. That feature comes in, I believe 2015 has it. So, without using constant expression, how do we do this? How do we do this dumb bullshit? That's the question. Now, the answer is there's a trick you can do, and the trick is called use a template. So here, I've got the same thing here, the Blit SSE source aligned, templated, and it basically breaks those things up into functions. and calls them. But as you can see, the alignment value, like I said, you can't pass it in a function parameter. But what you can do is you can use a template parameter to instantiate a template function at compile time, and that template parameter will be inserted as a constant that is known as at compile time, and then everything works. So what you do is, well, let me show you. Well, first of all, for the 0 case, all I did was I called the function that I wrote up here, which is draw blit SSE source destination aligned. So this is the case where everything is aligned perfectly. You just got to copy. So I'll just call that function here for case 0. Now for the other cases, I've got to do bullshit to align. So I got to prime the pump and all that other fun stuff. So what I do is I go down here and I create this template and I give it a parameter, which is an int parameter for the alignment. And this template function is a wrapper around the other one. All this one does is it contains the while loop, which loops through all the stuff here. And then for every row, it calls this one source aligned row template with the alignment. It passes this alignment parameter down to this template function. Go to definition here. And this one just has all that other stuff I explained before. So here you've got the alignment value. And that value we multiply by 4. Where is it? I can't find it. Here we go. We multiply the alignment by 4 to get the left shift value for the new source. And we take the complement, the 4's complement. I don't know if that's what you actually call it, but that's what I'm going to call it. And then we multiply that by 4 to get the shift value to the right for the previous source. And that's also the shift value here for the priming, the value priming bullshit here. So that's what we're doing. And this makes the code, you know, a lot nicer. And if we make a change to the algorithm, instead of having to change every instance in the switch statement, all we've got to do is change the template function, and that changes every instance already. So that is how we'll generally proceed when we have to do this dumb bullshit with constant expression values that we need. But in the future, when I switch over to 2015, someday I would like to try out the const expression without this template shenanigans. That's a word, right? I don't know. All right. So that is the case for when the source is already aligned. Now here, we do the same thing, but we use SSE3. And SSE3 gives us a nice function. Let's go to definition here, and we'll go to definition here. Take a look. So it gives us a function called alignr epi 8, which is which emits the instruction p-alignr. And what that does is that allows you to align two XMM registers together. So basically what it does is it does all of this shifting and masking bullshit, and it does it all at once for us. So let me just bring out a nice little layer. So let's say we've got two registers. We'll call them A, B, C, D, and W, X, Y, Z, and we go p-alignr, and we do some, let me think here. We'll call this one G, we'll call this one H, and we do p-alignr G, H, and 8. And what that'll do is it basically it concatenates G and H together, A, B, C, D, W, X, Y, Z, and then it takes an offset from the beginning here of this number here. So 8, the offset would be here. And it gives you the 128-bit value, which is in this window here. So the offset value slides this window around. And these two values determine what values make up the 256-bit concatenated value. So it allows you to basically slam two values together and then get any 128-bit window inside of your 256-bit concatenated value. So it does all that shifting and masking bullshit all in one shot, which is great. If you have it, it makes your alignment bullshit faster. But otherwise, this is exactly the same as what we had before. And it does the same bullshit. So that's just the SSE 3 version of that. Source aligned templated. SSE 3, source aligned templated. So now we get down to the thing that I wanted to do, which is I want these ones up until here, they have assumed that the source rectangle is pre-aligned. What we want is a function that makes no assumptions, that can work with any source, any destination. You call it, it just works. And that's going to require some extra bullshit. All right, so the first thing we do is we check to see whether our source is less than 4 pixels wide. Because if it's less than 4 pixels, we can't even get a single SSE transfer in there. And in that case, all we're going to do is just pass it on to our standard blit function, which, doesn't do any vector transfers or whatever. All it does is a very simple loop, and it copies the pixels. So if we're so tiny that it doesn't even matter, just call the standard function and be done with it. Now, if that's not the case, what we're going to do is we're going to check our source alignment on the left side and our source alignment on the right side. So this is basically doing is just rounding up and rounding down to the nearest 4 aligned x coordinate. And then what we're going to do is we're going to check to see if the original left and right are the same as the source aligned left and right. And if they are the same, all we do is we call our previously determined source aligned templated function. So if the source is already aligned, we can just call this simple function that we've already defined, and we'll delegate to that one. Now, if the source left and right, or either one of them is not aligned, then we first have to align the left and the right before we can call those functions. So then we first we get the alignment value for the destination x. Now I don't know what this thing here is for per se. This is adding to x. So this is the alignment of the destination after we have peeled away the unaligned parts of the source. So the difference between the aligned source x and the original source left is basically the width of the amount, the portion that has to be peeled. So we add that width to this x here to get the start in the destination of the source part that is aligned. Does that make any sense? It's kind of complicated. So that's the this calculation gets the start in the destination of the aligned start of the source, and this thing here just gets the alignment value of that x start. All right, and then we switch on that alignment value. And here we blit SSE destination aligned. So this means that it's already going to be aligned, that the destination is going to be aligned. And so our job will be easier. Otherwise, if the destination is not going to be aligned, then we're going to have to do a little bit more work. So let's look at the destination aligned part here. Now I'm kind of glossing. I'm not going into super detail. I'm not going to draw diagrams for every single little thing. So if you are interested at all in knowing more about some stuff that doesn't make any sense to you, feel free to ask any questions you need, and I will always be around to answer what you need to know. But to continue on, so here is where the destination is going to be aligned during our transfer. So in this case, what we're going to do is, first off, we're going to peel we're going to peel off the part of our source that is not aligned. So this is the loop peeling part that I was talking about in the beginning. We use loop peeling to correct our source alignment, and then we use the pump priming to correct our destination alignment. Now, this calculation here told us that after we peel the loop, the destination is going to be aligned. So we peel the loop, and now that we've peeled the source and the destination are aligned, and so we just call source destination aligned, which is just a very simple copying of values without any further bullshit. And then we peel the loop on the end if necessary, and then we're done. So that's the simple situation where after we do the loop peeling, this is the calculation to find the destination X after the loop peeling is done. And after we do the loop peeling, the alignment is 0. It's perfectly aligned. Now, if after we do the loop peeling, the alignment is not 0, then we're going to have to do our dumb bullshit with the priming of the pump and so forth. So we go here. Again, we peel the loop. We peel the parts of the source that aren't aligned. And then we call our row template function for the alignment here. And this is the same thing I showed you before. This is just where you prime the pump and then you do your alignment and all your fun bullshit, and Bob's your uncle. And that's it. That is basically it. Yes. So this part is basically the same as we had before. You've got your SSE template function, which contains your while loop, and which calls your row template function, which contains your X loop using pointer arithmetic. And it primes the pump with the destination values that won't be overwritten. And at the end, it finishes off the last section that contains destination pixels that will not be overwritten, using, again, the shifting and masking bullshit that I talked about before. And there you have it. That is all there is to be written about this function here. So let me take a look here. Where are we at? This one here, blit SSE. Now, blit SSE 3 is the exact same thing, only for the shifting and the masking, it uses the p-align r instruction instead of, shifting and masking. So it's a little faster. It's going to be a little bit faster than your other one. Let's just take a look at that for a second here. So let's make some comparisons. So I've got a little function. A little function called, what is it called? It's called make blit batch, and it just makes a bunch of rectangles and points for blitz, the blit to the screen, and it does such that there's no clipping involved, because our functions so far they don't take into account clipping. So what we're gonna do, we're gonna get rid of this draw rect, and we're gonna go. What are we gonna do? What are we gonna do? So let's try blit. So we'll try our standard blit, and we'll see how long it takes. The actual job, the vector of blit jobs that is created, we'll use you can specify in this function, you can specify a seed, and since 420 was exactly 4 days ago, I think it's a good number to use right now. Blaze it, 420. Is that a meme? Am I a memer? I'm a memer. I'm a schemer. I'm a Monday morning dreamer. That was a good rhyme. I hope you enjoyed. Oh, okay, yeah, that's fine. So here's our blitz. I don't know how many rectangles I've actually put in this blit job, but I can check up here. Where is it? 20. Let's up the ante just a little bit here. Let's go for 60 rectangles. We'll get a nice sample size here. So here's what it looks like. This is blitting using just a standard algorithm, and it gives us, wow. Okay, so it takes a long time, and that is why. Oh, and also we're in debug, which is probably not a good idea for doing a performance test. Just saying is all. So here's our stuff. We'll let it run for just a couple of seconds, and then we'll stop it. Check the log file. So yeah, we've got about 1.9-ish, 1.9 milliseconds. And let's try with blit SSE. Let it run for a little bit. And we'll check the log file. So 1.4. So you get a decent speed increase, but it's not huge. It's not like many times faster or anything. And the reason for that is, I mean, in general, just blitting, just copying to the memory is going to be fast. There's really no computation going on behind the scenes there. So you can't expect a huge speed increase in this situation. But you get a decent increase, if like 30% or something. I don't know how much you get, 20%, 30%, whatever. You get some increase here. Now, what is interesting to note is blit SSE is going to be considerably faster when the source and the destination are aligned. So if you're copying from aligned portions and you're also copying two aligned portions of memory, you're going to get a lot of better increase. Whereas the standard blit, there's no difference there. Now, we can use blit SSE3. So this one was giving us what? It's kind of all over the place, but let's say in general 1.5, 1.5-ish, 1.55. Somewhere around that region. If we try to do with blit SSE3, take a look at that. Yeah, we'll reload that. Now you've got like 1.4, 1.4 something. You get a little bit of an increase. Nothing to write home about, but shaves maybe 10% off of your runtime by using the plinr instruction. A little bit of a boost, nothing to write home about. Let's take a look at something else here. Now is the time where I let the cat out of the bag, basically. Because there are instructions for SSE that allow you to load and store from unaligned addresses that are not aligned. And these ones, I mean, obviously you don't have to do any alignment bullshit for them, except at the end, if you're the last number of pixels that you have is not 4, then you're going to have to copy them individually or do something else. Right? But if your width is a multiple of 4, you don't have to do anything special. You just load and store and you're done. So that is obviously a lot easier. I mean, look at all the bullshit we had to go through here. We've got a function to handle just standard if it's just less than 4 pixels wide. We've got a function here to handle if the alignment, the source is already pre-aligned. And then we've got a function here to handle if the destination is always already pre-aligned. And then we've got a function here, a template function, that calls another template function that does a bunch of dumb bullshit to align our bullshit. And that is obviously a big pain in the ass compared to this. This calls no other functions, it's just everything is right in here. Well, except for the case where you have less than 4 pixels. Obviously that's a special case. But outside of that, this is super simple. So, the question is, why wouldn't you always use this? Why would you ever use anything but this? And the answer is in general, loading and storing from unaligned addresses is slower than doing it from aligned addresses. Now here's the thing. Back in the day, back with older CPUs, like for example, let's say even like a Core 2, there would be a very large penalty for using store U and load U. And the penalty would be so great that it's basically, you shouldn't use them ever. You should always try to align the addresses yourself and then use the standard store and load. But in recent years, I think starting with maybe Ivy Bridge or I don't know what architecture, Intel made the logic for store U and load U much better. So now, in general, from what I can see, compared to fixing up yourself, store U and load U actually faster. Not just like the same or a little slower. It's actually faster. So let's look at this SSE 3 thing. We've got about, 1.45 maybe? It's all over the place, but let's just say 1.45 for the record. Now let's go blit SSEU. Build that. Let it run for a couple seconds. Yeah, I do want to reload it. And now we're down to 1.3, 1.4-ish. It's all over the place, but in general I'd say 1.3. So, for all of the work that we took, it's still faster to take the easy way out and use this. But the thing is, that was not always the case. So, the question is, what CPU are you coding for? If you're coding for an older CPU, then you should probably do all this bullshit if you want to get the maximum performance. But if you're coding for a newer CPU, then doing this bullshit is actually a little bit slower than taking the easy way out. So that is one question that you're going to have to ask yourself. Now, the optimum solution here, the best thing you would want to do is code both, and when the program starts, or when the program installs in the first start, you run a benchmark, check to see which is faster, and then you write in a configuration file, use unaligned blit or use aligned blit or whatever. That is the optimum solution. But I mean, that's a huge pain in the ass. So probably, newer CPUs, they're probably not going to go back to the old way of doing things. So it's probably, unaligned access is probably not going to get slow again. But it depends. The thing is the question is, what is your motivation for writing these optimized routines? If your motivation for writing optimized routines is to allow the greatest number of people to enjoy your game, then you want to focus on the people with the shittiest hardware for your optimization, because you want to bring them up. Focusing on the people who already have newer CPUs is just it's a win more situation. It's giving the winners just a bigger win, but it's not bringing the losers up anymore. So there's a philosophy in that. The best thing to do would be to write both algorithms and then benchmark them at runtime. But like I said, that's a big pain in the ass. And what I'm thinking is that these days, the CPUs that have the slow unaligned access, they're getting fewer and fewer. So you could probably forget about them. Now, I don't know about people with, like, for example, Intel Atom processors, or, low-end Celeron grade processors, or even like i3. I don't know where the cutoff is. You'd have to look into that yourself. But all I know is that in the higher end CPUs, the mid to high end range, CPUs that can't do unaligned fast are getting fewer and fewer. So you have to look into that yourself. You got to weigh all of the different variables to decide what algorithms you're going to put in, how much effort you need to put in. But if you're looking at this and you're saying, I am not going to do all this bullshit, then you might as well just do this one, because it'll give you a speed up in either case, and in most cases, it's just going to get better as time goes on, and people keep ditching their old ass CPUs. So that is my tirade about the CPU architecture evolutions and whatever. Now there is one thing that we can do here, and the thing is, here we're doing unaligned stores and unaligned loads, and at the end we're using loop peeling to fix up the last few pixels that didn't fit into a full SSE load store. Now, we can do better than this. Just because we use the unaligned addresses doesn't mean that alignment doesn't matter. Unaligned is still going to be faster. This instruction here is still going to be faster if we do it from an aligned address rather than an unaligned. If we do it from an aligned address, it's going to be the same speed as as this thing here. It'll be the same speed as this. But in an unaligned address, it's going to be slower. That doesn't change. So what we can do, remember the whole problem was that our source and our destination were out of phase with each other. We didn't have that problem when we only had to deal with a destination. And the same thing is true for our blitting. All we need to do really is use unaligned on one of either the source or the destination, and then we can use aligned on the other. So instead of just saying, fuck it, I don't care, just do unaligned with everything, we put a little bit of work in. We make it so that, well, for example, in this function, the destination is aligned. So this is an unaligned blit, but the destination is aligned. So we do loop peeling at the beginning and at the end to handle the parts of the destination that aren't aligned. And in the loop here, in the main loop, we only do aligned stores to the destination, but our loads are unaligned. And in that case, let's take a look at our speed. So here, destination is aligned. So for both unaligned, we're getting about I don't know what to call this. Let's just call this 1.336. 1.36. Remember that number. SSEU destination aligned. Build. We run that. Stop it. So that was 1.36, right? Now we'll go to log file. We're down even better. 1.241, 1.24. So by aligning to the destination, we have improved our lot in life. Now we can do the same thing, but we can align to the source. Let's just take a look at what we had here. Let's say this is 1.28. So now we'll go source align. Remember, we can't align both. It's just not going to work. But we can get one or the other. So we had 1.28 before. Now what do we get? 1.3738, 1.4. So it looks like for this one, is this source aligned? I'm a little bit confused now. I'm going to definition. Store unaligned. Yeah, source is aligned in this one. So it seems like destination aligned is better. Now it'll depend on your situation, which is going to be faster. I'm actually a little surprised with this result, but whatever. I don't want to make this video too long, so I'm not going to go into the details. But basically, either way, aligning one of them is better than just saying fuck it and not aligning anything. All right. Now the last thing that I want to talk about here in this video is we're going to do the same thing, but we're not going to do blitting. We're going to be doing alpha blitting. So we're going to use the alpha algorithms that we developed up here in the full screen filters, but we're going to be applying them to the blitting. So again, we can try it with source and destination. Here is basically just the blitting stuff here. And I'm using the SSE3 version. So that uses the P-Shuff-B, the shuffle here, to do the unpacking and the broadcasting of the alpha channels. And yeah, that's just the blending part. I create a lambda function to handle the blending. And then I call that lambda function down in here. Now, for the what is it called? The loop peeling, I just use the standard, what do you call it? Not vector, but scalar alpha blending function here. I could have created a separate function, but I just instead copied and pasted this, which is probably not a good idea, but I was feeling lazy at the time. All right, so yeah, we just do the same basic thing, only we use blending. We blend, so we got to load the destination and the source, blend them together, and then we store them back in the destination. And you've got a source version, you got a destination version. One is faster than the other. I believe doing it with the destination aligned is faster in this case as well. It surprised me that it was faster in this case, but this case it makes sense that it's faster. Destination, because you've got to load from the destination to do the blend, and then you've got to store back to it. So it's a good idea. The thing you're going to do, load, store, make that thing the aligned thing. And so that's all there is to this. It's basically just the same as the blitting, only you've got the alpha blending stuff built in there. And just for completion's sake, I did the the aligned algorithm, but for blit alpha, which caused me to have to rewrite all that bullshit up there, only with alpha pre-multiplied versions. And that, let me just say, that was a pain in the ass. But it's basically the same as what you have before, except for maybe one or two little differences. And let me just check here. Alpha pre-multiplied source aligned row template. We're getting into the long function names now, friends. Go to definition here. Yeah, this was a little tricky. I think the tricky part was, for me, figuring out that when you prime the pump, you can't just load the destination and then put them together and then store, because you're doing a blend operation in the main thing here. So to prime the pump, we actually prime it just with transparent pixels. And doing that means that the parts, the beginning of this loop here, is not going to write those pixels to the source. So it's just going to keep the source. But otherwise, it's basically just the same. And I do a little trick here. FF, in our case, because when we pre-multiply, the alpha value is actually the alpha complement. And so FF means that take all of the destination, none of the source. Now to load FF into all the alpha, and we just load it into every pixel value, we can use a trick by comparing a value to itself, that the result of that is just all ones, because when you compare anything to itself, it's going to be equal. And when the values are equal, it just puts all ones in the destination register. The corresponding position in the destination becomes all ones when the values are equal. So we do that trick. We compare a value to itself. Just any value is okay. And doing that will give us a value that's just all ones. And we won't have to load from memory. And that's just a little bit faster. It's just a little trick of programming. Just like if you want to zero out a value, you exclusive OR the value with itself. This is to put all ones in the value, all binary ones. So, but that's all you got here. So this part is a little different than in the blitting version, but otherwise pretty much the same. But it took me a while to debug all this bullshit. It was an enormous pain in the ass for really no gain, because I mean there's certain situations where you'd want to use this one, but basically not this one. Where is it? Where you'd want to use this one. But basically you're going to want to use one of these, probably this one. So let's compare blit alpha pre-multiplied with all of the blit alpha. I believe that is the name. No, that is not the name of the function. Okay, well, fuck me, I guess, then. Blit alpha pre-multiplied packed is the correct name of the function, apparently. This is just a standard one. With a little bit of optimization, but no SSE. So we'll build that. Now we're doing alpha blending. So there you go. We'll let it run for just a little bit, and we'll take a look at the times. Now, this is obviously a lot slower than just a standard blit, because we're doing a bunch of calculation. So here we've got basically, what, 9? I'm seeing about 9 here. We'll just say 9 milliseconds. And now let's take a look at the blit alpha pre-multiplied. I'll just delete all this. It's faster. Blit alpha pre-multiplied. That's blend. We want blit. Alpha pre-multiplied. destination aligned. There we go. This is probably, I believe, the fastest one we have. So the non-SSE gave us 9 milliseconds. SSE gives us 1.92, gives us about 2 milliseconds. So, we're over 3 times faster now. And that is the kind of speed increase that we would expect from SSE. We didn't get the much increase with the blitting because there wasn't much calculation involved. It was just moving the memory. The bottleneck was the memory. Here, the bottleneck becomes the calculation. And thus, SSE gets a huge advantage. So that was about 2 milliseconds. Let's try with our aligned version. See what we get. I'm guessing it's going to be somewhat slower. 10%, 20%, I don't know. 2.1, 2.2. So yeah, you're getting, between 5 and 10% slower maybe. Maybe like 7% slower. I don't know what the numbers are. But it's a little bit slower if you do it yourself rather than you let the unaligned axis instruction do the alignment for you. And just for completion's sake, these functions are fine, but if you try to draw off the edge of the screen, you're going to get fucked. So what you want to do, and this is easy. This is not what I want to look at. I want to go to surface. What you want to do is you want to pick one of these functions and you want to clip. You want to adjust the source rectangle and the destination point such that you're going to be drawing within the region specified by your clipping rectangle. So you can just do a few quick tests and adjustments here. I'm not going to explain this. I've covered this before. And then you call the unclipped version of the function, and Bob is your uncle. And that works. I've tested this function out. I could quickly go over here, and where's the here? And I could go make blit batch 2. This one generates blit commands or blit data that goes off the screen. And by doing so, and by going into here and going, let's just go back here. Blit. And where's the clipping one? There's gotta be a clip one here. Blit alpha pre-multiplied destination unaligned destination aligned clip. Not too long at all. Perfect length for a function name. There we go. Clipping. Add the clipping rectangle there. And start without debugging. And there you go. You've got rectangles which appear to be going off the screen. We can't, tell exactly whether they are or not, but they probably are. And we'll stop that. Take a look at the log file. The values are lower because obviously we're not going to be drawing all of the rectangles that we were before. We're just drawing portions of them because some of them are going off the screen. But you get the idea. This is the end result of something that you could use in an actual game if you were using, you were limiting yourself to not using the graphics card to draw, which you normally wouldn't. But like I said before when I started this, these functions, are not meant in general to be used in a game engine. You could use them and they're very fast, but they can't beat what the actual graphics card would be doing by just firing triangles onto the screen, textured triangles. So the main reason why I did all this bullshit was just to teach people how to use SSE, because there's not a lot of material on the internet about this and on YouTube. No explanations on how to actually realize real functions in SSE. And that's why I did that. And that's why I talked about this alignment bullshit, because it's important, even though it is an incredible pain in the ass. And even though you have access to those unaligned stores and loads, and you could basically ignore all the bullshit that I talked about, you still get the best performance by trying to do your best job and aligning at least one part of your data processing bullshit. So that's why I talked about it. I did the job. I did the hard thing. Even though I wanted to do the easy thing, I did the hard thing, and I feel better for it. And you will feel better for it too. But that is all we have for today. And basically, this is everything I needed to teach so that I could talk about the blending, the Bloom algorithm that we're going to be using in the Hugs series. So the optimized Bloom is going to be using SSE, and it's basically going to be using all of the stuff that I've taught up until this lesson. Now, I think I'm going to do one more lesson about integer SSE, and that's going to be about masking and branching. It's going to be a little bit about SSE and a little bit about branch prediction and how the CPU does that. And that'll be the last thing I talk about in integer SSE. But I might do more SSE after that, but it'll be, it won't be integer, it'll be floating point stuff, which is also incredibly useful. Probably more common to do floating point SSE than to do integer. The reason why I wanted to tackle integer was because you don't see much information about it on the internet. It's a much less common skill that people have. So that's why I tackled it first. But yeah, so next hand relief episode will be about branching, and especially branching and how it relates to SSE. And after that, maybe some floating point stuff. We'll see. We will see. But until then, I'm Chili signing off, and I will see you in the next Hugs episode, I guess. Ta-ta.